Ships that are designed to carry liquefied gas have become more significant and increased in number in the recent years, with the increasing need for alternative fuel. The two main types of liquefied gas carriers are LPG, liquefied petroleum gas carriers, and LNG, liquefied natural gas carriers. To understand the design characteristics of these two types of ships, we first need to know a few notable details about the composition and properties of LPG and LNG. Liquefied petroleum gas, LPG. Petroleum hydrocarbon products such as propane and butane, and mixtures of both, have been categorized by the oil industry as LPG. It is widely used in domestic and industrial purposes today. The most important property of LPG is that it is suitable for being pressurized into liquid form and transported. But there are conditions related to pressure and temperature that need to be maintained for the above to be carried out without posing threat to life, environment, and cargo. At least one of the following conditions need to be complied with for transportation of LPG. The gas should be pressurized at ambient temperature. The gas should be fully refrigerated at its boiling point. Boiling point of LPG ranges from 30 degrees Celsius to 48 degrees Celsius. This condition is called fully refrigerated condition. The gas must be semi-refrigerated to a reduced temperature and pressurized. We will see, at a later stage, how the above conditions affect the design of different types of LPG tankers. Other gases such as ammonia, ethylene, and propylene are also transported in liquefied form in LPG carriers. Ethylene, however, has a lower boiling point, 104 degrees Celsius, than other LPGs. Hence it must be carried in semi-refrigerated or fully refrigerated conditions. Liquefied natural gas, LNG, natural gas from which impurities like sulfur and carbon dioxide have been removed, is called liquefied natural gas. After removal of impurities, it is cooled to its boiling point, 165 degrees Celsius, at or almost at atmospheric pressure. Note here that unlike LPG, LNG is cooled to low temperatures but not pressurized much above atmospheric pressure. This is what makes the design of LNG carriers slightly different from LPG carriers. LNG, at this condition, is transported as liquid methane. Today, most fully pressurized ocean-going LPG carriers are fitted with 2 or 3 horizontal, cylindrical, or spherical cargo tanks and have typical capacities between 20,000 and 90,000 cubic meters and length overall ranging from 140 meters to 229 meters. New LPG carrier ships are designed for dual-fuel propulsion system possessing the ability to utilize LPG or diesel fuel on a selective basis. Fully pressurized ships are still being built in numbers and represent a cost-effective, simple way of moving LPG to and from smaller gas terminals. are built to carry liquefied gases at low temperature and atmospheric pressure between terminals equipped with fully refrigerated storage tanks. However, discharge through a booster pump and cargo heater makes it passable to discharge to pressurized tanks too. The first purpose-built LPG tanker was the M/T Rasmus Falstrup from a Swedish shipyard to a Danish design. Prismatic tanks enabled the ship's cargo carrying capacity to be maximized, thus making fully refrigerated ships highly suitable for carrying large volumes of cargo such as LPG, ammonia, and vinyl chloride over long distances. Today, fully refrigerated ships range in capacity from 20,000 to 100,000 cubic meters. LPG carriers in the 50,000–80,000 cubic meter size range are often referred to as VLGCs. Although LNG carriers are often larger in terms of cubic capacity, this term is normally only applied to fully refrigerated LPG carriers. The main type of cargo containment system utilized on board modern fully refrigerated ships are independent tanks with rigid foam insulation. The insulation used is quite commonly polyurethane foam. Older ships can have independent tanks with loosely filled perlite insulation. In the past, there have been a few fully refrigerated ships built with semi-membrane or integral tanks and internal insulation tanks, but these systems have only maintained minimal interest. The large majority of such ships currently in service have been constructed by shipbuilders in Japan and Korea. In November 2018, South Korean shipbuilders locked in 3 years' worth of large-scale LNG carrier contracts, more than 50 orders, with a value of $9 billion. South Korean builders captured 78% of LNG-related shipbuilding contracts in 2018, with 14% going to Japanese builders and 8% going to Chinese builders. The new contracts would boost the global LNG fleet by 10%. Of the global fleet, historically, about 2/3 of the ships have been built by South Koreans, 22% by Japanese, 7% by Chinese, and the rest built by a combination of France, Spain, and the United States. South Korea's success stems from innovation and price point. South Korean builders introduced the first icebreaker-type LNG vessels, and South Korean builders have been successful in catering to increased customer preference for Q-Max vessels over MOS type. number of gas carriers have increased drastically over the last 10 years, owing to the increasing need for alternative fuel. These are usually high-speed ships with fine hull form, which makes it passable for extensive research opportunities to improve on hull efficiencies in order to achieve more power efficiency. A lot of research is also being carried out to design advanced cargo containment systems, and concepts of adjoining bunkering systems are being developed by various countries that are opening themselves to extensive use of natural gas. Today, not all shipyards are equipped to design and build specialized ships like LPG and LNG carriers. This leaves a wide scope for designers and shipbuilders to develop skills and infrastructure to specialize in building these ships. Since LPG, LNG carriers are low-speed vessels, average maximum cruising speed is 15.5 knots, and are not restricted by space constraints, they can afford to be run by large slow-speed marine diesel engines. These engines occupy more space than high-speed marine diesel engines, but provided more shaft efficiency, and gearbox losses are eradicated since the RPM of the engine is same as that of the propeller. Usually, large diameter and low RPM propellers are used for more propulsive efficiency. LPG, liquefied petroleum gas, and LNG, liquefied natural gas, carriers play a crucial role in the global energy supply chain by transporting these liquefied gases from production sources to distribution points and end users. Here are some key points highlighting the importance of LPG and LNG carriers. Efficient transportation. LPG and LNG are gases that can be liquefied for easier and more efficient transportation. Liquefaction reduces the volume of these gases significantly, making it practical and cost-effective to transport them over long distances. Global energy trade. LPG and LNG carriers facilitate the global trade of energy resources. These carriers transport liquefied gases from regions with surplus production to areas with high demand, helping to balance energy markets and ensuring a stable energy supply. Diverse energy sources. LPG and LNG are versatile energy sources that can be used for various applications, including heating, cooking, power generation, and as a fuel for transportation. LPG is commonly used for residential and commercial purposes, while LNG is often used for large-scale industrial applications and as a fuel for ships. Energy security. The ability to transport LPG and LNG globally contributes to energy security by diversifying energy sources and reducing dependency on a single region for supply. This helps countries to mitigate the impact of supply disruptions and ensures a more reliable and resilient energy infrastructure. Environmental benefits. The use of LPG and LNG as fuels offers environmental benefits compared to traditional fossil fuels. They produce lower emissions of pollutants such as sulfur oxides, SOx, nitrogen oxides, NOx, and particulate matter, contributing to efforts to reduce air pollution and combat climate change. Infrastructure development. The demand for LPG and LNG has led to the development of specialized infrastructure, including liquefaction plants, storage facilities, and dedicated terminals for loading and unloading carriers. This infrastructure supports economic development and job creation in regions involved in the production and export of these gases. Economic impact. The LPG and LNG industry has a significant economic impact, creating jobs in various sectors, including exploration, production, transportation, and distribution. It also stimulates economic activities in regions that are major exporters of these gases. Safety standards and innovation. Due to the unique challenges associated with handling and transporting liquefied gases, the industry places a strong emphasis on safety. This has driven the development of advanced safety standards, technologies, and practices, leading to continuous innovation in the design and operation of LPG and LNG carriers. In summary, LPG and LNG carriers are vital components of the global energy infrastructure, playing a crucial role in ensuring the efficient, safe, and reliable transportation of liquefied gases to meet the diverse energy needs of communities and industries around the world. The use of natural gas as a primary energy source will remain vital for decades to come. This applies to industrialized, emerging countries and developing countries. Owing to the low level of impurities, natural gas is considered to be a climate-friendly fossil fuel because of the low CO2 emissions, but is at the same time an affordable source of energy. In order to enable transport over long distances and oceans, and hence create an economic and political alternative to pipelines, the gas is liquefied, which is accompanied by a considerable reduction in volume and then transported by ship. Thus, at international ports, many LNG tanks are required for temporary storage and further use. The construction of LNG, liquefied natural gas, storage tanks is a complex process that involves adherence to strict safety and engineering standards. LNG is stored at extremely low temperatures, typically around 162 degrees Celsius, 260 degrees Fahrenheit, which requires specialized construction techniques and materials to ensure the integrity and safety of the storage facility. Here's an overview of the general steps involved in the construction of LNG storage tanks. Site selection. Selecting an appropriate site for the LNG storage facility is crucial. Considerations include proximity to natural gas sources, accessibility for transportation, safety regulations, and environmental impact assessments. Prepare the site by excavating the foundation. The foundation must be stable and able to support the weight of the LNG tank. Construction of outer tank. Pit construction. The outer tank is constructed first and serves as a barrier for insulation. This tank is typically made of reinforced concrete or 9% nickel steel. The pit is lined with insulation materials to minimize heat transfer. Inner tank construction. The inner tank, which directly holds the LNG, is constructed inside the outer tank. This tank is made of special materials, such as 9% nickel steel or aluminum alloys, to withstand the extremely low temperatures. Insulation. Apply multiple layers of high-quality insulation materials to the inner tank to minimize heat transfer and maintain the low temperature required for LNG storage. Safety systems installation. Install safety systems, including emergency shutdown systems, pressure relief systems, and fire protection systems. These systems are critical for ensuring the safety of the facility. Testing and quality assurance. Conduct thorough testing, including leak tests, pressure tests, and inspections, to ensure the integrity of the tank and its components. Quality assurance processes are essential throughout the construction phase. Commissioning. Once construction is complete and all safety checks are successful, the LNG storage tank is commissioned for operation. This involves introducing LNG into the tank and ensuring that all systems function as intended. Operation and maintenance. Implement a comprehensive maintenance and inspection program to ensure the ongoing safety and efficiency of the LNG storage facility. It's important to note that the construction process may vary based on the specific design, location, and regulations governing the project. Working with experienced engineering and construction professionals familiar with LNG storage tank projects is crucial for a successful and safe outcome.